Hello everyone. Today we will look into evaluating functions and function form. Function form is writing a function in y is equal to mx plus b style. We have couple different type of functions. One of them is a discrete function. A discrete function that has a few x and y values. It may look like scattered or in a pattern, but the points are not connected. If you see a graph where you have couple points in different places, and if it's a function, this will be an example of a discrete function. Again, a discrete function will have points that are not connected to each other. Points may appear in a pattern, but it will still not going to be connected. We call these type of functions as discrete functions. The second type is continuous function. A continuous function is a function that has connected points and it looks like a line or a curve. So you may see a line like this, and it has many ordered pairs, and because it has infinitely many ordered pairs, it looks like a solid line. You may actually see a curve as a function as well. Go ahead and pause your video and write down your notes. Our next type is a constant function. A constant function where each x value is paired with the same y value. When each x value is paired with same y value, on this one 2, 4, 6 are all paired with positive 2, and I can continue that way as well. This would be an example of a discrete function and is also a constant function. We could have a constant function where all the x values would be paired with the same y value, and it could be a continuous function as well. When we see a graph where the graph doesn't pass the vertical line test, if I have a shape like this and if I do my vertical line test, I can see that the line is touching to the graph at least at 2 different points, so this is not a function. We could have a discrete function that's not a function, where you would have couple points on the graph, and if at least one of the points is not passing the vertical line test, then it's not a function. Now let's look into evaluating functions. In order to evaluate functions, we will think of this function as y is equal to 4 minus 3x style. And in our example, f of negative 3 is being asked. F of negative 3, this is the x value, and what we find will be the y value. We want to substitute the x value into the equation, and we will find the corresponding y value. If I substitute negative 3 for x, make sure to put a parenthesis around negative when you substitute. Now I will have y is equal to 4 minus negative 9. Subtracting negative is addition, so y would be equal to 13. From this, I can get two type of answers. F of negative 3 is equal to 13, or I can write this as an ordered pair where negative 3 and 13 are ordered pair. On an ordered pair, we have x and y values. In a function form, what's inside of the function is x. What's the result of the function will be the y value. Here's your u-try. Remember your x and y values and substitute. Here's our second example. On this example, instead of having a given x value and evaluating, this time we don't know the x value. Instead, we have the y value given. I can rewrite my function as y is equal to 4 minus 3x style. And in this case, f of x is equal to 16. So instead of writing f of x, I can just write 16, and that part must be equal to 4 minus 3x. We are going to find the x value that makes this function true. So in order to do that, we will solve for x, subtract 4 from each side. We will have 12 is equal to negative 3x. Then I'll divide each side by negative 3, divide each side by negative 3. X will be equal to negative 4. Again, I can write my answer in two different types. I can write f of negative 4 is equal to 16. This would be the function form. I can write as ordered pair, negative 4 and 16 would be a point on the graph of this function. And our answer is x is equal to negative 4 here. Here's your u-try. Remember that you have the x value already. Excuse me, you are looking for the x value, you have the y value already. And find the x value that will make this function equal to negative 5. Let's do one last example of this type of evaluating for the x value. If I have the function f of x is equal to negative 1, so f of x is equal to negative 1. Instead of f of x, I substitute negative 1. We will have 1/3 x plus 2. In order to solve for x, I will undo addition and subtraction first. Subtract 2 from each side. Negative 1 minus 2 is negative 3 is equal to 1/3 x. In order to get rid of the fraction, I will multiply each side by the denominator, each side by 3. I'll have negative 9 is equal to x. So x value we're looking for is negative 9. I can write f of negative 9 equals negative 1, or I can do negative 9 and negative 1 as ordered pair. In the function, I have x is inside, y next. On the ordered pair, x is first, y is next, just like in the alphabet. Here's your u-try. Now, before we start on this side, let me tell you a joke. How do you make 7 even?
I don't know. How do you make 7 even?
You drop the s. Okay. Tomorrow, somewhere on your paper, put even 7, so we will know that you actually watched the video and enjoyed our joke. Even 7. Now let's look into something called set builder notation. Set builder notation uses x such that x belongs to an interval, or we can use a list notation. But let's first find our domain and range, and we can use set builder notation for our domain and range. In our question, we need to identify whether this is a function or not. When I draw my vertical line, and vertical lines will not touch the graph more than one point at a time, so this will be a function, it passes the vertical line test. Now let's think about the x and y values that are on the graph. The graph consists of ordered pairs. Each of the ordered pairs has an x and y value. And for all of those, we can list x values for domain, we can list y values for range. When I look at these values, the function continues to infinity on both ends, and our domain x values we can use on this graph are also going to continue to both negative infinity direction and positive infinity direction. So our domain for the x would be negative infinity till positive infinity. Range is also calculated the same way. I will look at the y values from the ordered pairs that are on the graph, and since all the y values are going down on both ends, it's going to go all the way to negative infinity. Y values are stopping at exactly 3, so it will not go past 3. Negative infinity till 3 is going to be our range. Whenever we have a value we can actually use in the function, we will use square brackets, and for the values we cannot use in the function, we will use regular parentheses. Because we don't know the values of negative infinity or positive infinity, I won't be able to use them in my function as actual numbers, so I will use regular parentheses for those. 3 is an actual number that we can get from this function for our range, so we use a square bracket for it. Now let's write these with set builder notation as well. For domain, I will do x such that x belongs to this group, negative infinity till positive infinity. We are done writing the domain in set builder notation. We can do the same thing for range. Range would be y values such that y belongs to, this time I will do negative infinity till positive 3. Whenever we are writing our intervals, we try to write them in a least to greatest order. Let's also calculate what will be the value of this function when x is equal to 0. When x is equal to 0, we look at x0 and then go to the graph from that and find the corresponding y value from the graph. Corresponding y value is 3. So result for this would be 3. Let's continue with the next example. I have a couple points here. I can check to see if it's a function by using my vertical line test. If I move my line left to right or right to left, I will not touch 2 points at a time. So this is, yes, a function. Next, let's look at the domain. Since this is a discrete function where points are scattered, our domain is going to be a list of numbers. I will start listing my points. This is -4, -3. I have -2, 1, 1, -2, 2, 3, and 3, -2. Our domains are x values, -4, -2, 1, 2, 3. I try to write my list in least to greatest order. For range values, I will list everything for the every y value for the range, same style, -3, -2, I have -2 twice, so I don't have to repeat that, and +1 and +3. These are my y values, close brackets. We can write our domain and range same way with the set notation. Domain would be x belongs x such that x belongs to this squiggle bracket, and I have -4, -2, 1, 2, and 3. For range, we will do range such that range values y such that y belongs to squiggle bracket, list all your items back again, -3, -2, 1, and 3. We are done listing our domain and range in set builder notation. Now let's evaluate the last part of this question where we have f of x is equal to -3. -3 is the y value. I look at all the points and then see in which the y value is -3. After finding that, I will identify the x value as -4. So answer for the x for that question is going to be -4. Here's our next one. I have x, is this a function or not? Once I see repeating x values, I check to see whether these x values are paired with same number or different number. Because an x value is trying to go to two different numbers, it's not a function, so I'll put a no for it. Even though it's not a function, I can still list the domain and range, and our domain values would be squiggle bracket 2, 4, and 10. I don't have to repeat the repeated terms again. For range, I will list the range as 0, 2, 3, and 5. F of 4, although this is not a function, let's make this R. R of 4, a relation. 4 is equal to 3, so answer for that part would be 3. I'm going to leave writing the domain and range in set notation for this one for you. We will look at the next example now. Here's our example 4. On this one we have restricted domain. Whenever our function doesn't continue to infinity on both ends, it means we have restricted domain. When we have restricted domain, it works the same way. We look at all the x values and y values, all the ordered pairs that are on the function. And in this case, our function goes to infinity on one end and it's stopped on the other. Whenever we are listing our x and y values, we will, let's start with domain. Domain values consist of x's such that x belongs to. Now let's decide in which interval the x values will be located. When I look at my graph, the graph starts from -3 right here, and then continues this way. All the x values, -3 and up, are used in this graph. So I will use -3 and up to infinity. -3 is an actual value we can use in this function. It's shown as a filled point, and infinity is a value we don't know, so we cannot use in our function. So I will use an open bracket for that, regular parenthesis for that. Range values work the same way. I will look at all my ordered pairs. Among the ordered pairs, we will look into the y values, and y values are between +3 and -infinity. Y belongs to +3 and -infinity. I will write this part in least to greatest order. So -infinity comes first, and then the 3. Infinity is parenthesis, 3 is square bracket. Here's your U-try. Make sure to write your domain and range in set builder notation. On this example, I have domain restriction on both ends, and I will look at all the ordered pairs on the graph. There are infinitely many ordered pairs, even if it's a small graph. When we have a closed end filled point, that means this point is included. Whenever we have an open circle, that means that point is not included in our domain or range. So in order to write our domain, we will start with x such that x belongs to. Now let's decide the interval the x values are located. X values starts from -4 and then it continues up to +4. -4 till +4. And -4 is a point that's filled in and actually used. And +4 is an open circle. That means that point is not used in the function. So it kind of works like this, where you have a filled point is square bracket, open point for regular parenthesis. Let's do the same thing for y value, range, y values such that y belongs to. Y values are between -4 and +4. -4 is an included point, +4 is a not included point. Here's your U-try next. Write your domain and range in set builder notation. Pay attention to your domain restriction and write the domain and range in least to greatest order. Last example and U-try. We have function values and we have a graph given. After you have a given graph, you can figure out the function values by just looking at the graph. In a given function f of 3 here, that means when x is 3, what is the y value? That's what we are looking for. When x is 3, I go to x is equal to 3 first, and then find the graph from that point, and go back to y coordinate to find the corresponding point. That would be -2. So x coordinate, y coordinate, I will start from x. Let's do the next one with -1. When x is -1, I'm right here. We will go to the graph first. From graph, go back to the y coordinate, and that's the point we were looking for. So whenever x is -1, y is going to be +2. Same process works whenever we are going backwards to find the x value. f of x is equal to -1. When y value is -1, what's the x value? That's what we are looking for. When y is -1, go to -1 on the y-axis, and then find the graph, go to the corresponding x coordinate, and x would be +2. Same way, when y is +2, go to +2 on your graph, find the point on the graph and find the corresponding x value. X would be -1. That's pretty much it. If you have any questions, please make sure to bring it to the class.